I forgot to record. Dima saved my life. Thank you so much. Otherwise, I would have done it after I finish, which is like I have 6 classes today, 6 hours of class. This is thank you so much. So I would just read this dy by dx, the derivative of y with respect to x. In this section, we consider the ratio dy by dx. We're going to treat dy as a segment, dx as a segment, just different ratio of numbers, right? And then we call dy and dx both differentials. We are calling any dz is a differential, dt is a differential, d theta is a differential, the most common ones. So we want to see the difference in equality of dy delta y and dx and delta x. Okay, so that is one scenario of a secant, like, you know. So what are the coordinates? Let's configure the coordinates of q. The coordinates of q has coordinate, the first coordinate is x plus delta x. Then the y coordinate is, see, for any change in x of, this is a side effect. So for any change in x, for any change in x, it produces a change in y. So this is actually y plus delta y. Right? So here it is y plus delta y. Right? This much is delta y. So is this one. If you make a triangle here, this is delta y. What is this? This is delta x. Right? You know the segments now. This is change in y. This is change in x. Delta y is nothing but change in y. Delta x is change in x. Okay. Now let's consider another way, another line which has dy by dx, which is what? The tangent line to the curve at any point. Let's call it p equal to that. By the way, this q is right there. Q, it has this dimension. What is this called? This is, as we call y as a function of x, you know, this is called f of x plus delta x. Isn't it the same? The value of the function at the x component, right? So now let's consider with a different color, let's consider a tangent line at that point. The tangent line at the point P. It touches the curve only at one point. So you see, this y is a tangent, like this line is. This is a tangent line, not a secant line. The tangent line, you can see what is, see, if you consider this, if you consider this triangle, what is the slope of that? Well, by the way, delta y is, this is delta y. Maybe I should write red. This is delta y. But this is what? Who can tell me what that green line segment is? If you consider that small triangle. Sivan, y? Y or dy?
Yeah, the slope is dy the differential
Yes.
is the derivative, right?
Yes. So it must be dy, right? Okay, what is the slope of that green line, the tangent line? In theory, the slope of the tangent line is dy by dx, isn't it? So for the tangent line, the slope is actually, by definition, dy by dx. So this must be the rise. This must be the run for the tangent line. So the rise is actually, this is dy then. So what is the run? This is the run, which is dx. Dx and delta x are exactly the same. Because in that triangle, the rise over the run for that green line and that small triangle is dy by dx. So therefore, you can see that delta y is not equal to dy from our picture, from the picture. I hope you follow me. So from the figure above, we can see that delta y and dy are not the same. Delta y is the ratio on top of the slope of the secant line. dy is the ratio on top of the slope of the tangent line. So they are not equal. We are talking about this distance versus this distance. This is dy, this is delta y. This is what we see from there, right? Now, but delta x and dx are the same because they are the run on the both on the x-axis. So, but delta x and dx, the change in x and dx are the same. Equal, it's right. But delta x equal to dx. Okay, that's all. So, but if you make this q, if q approaches p, if it's moving towards p, see the distance between the two is getting smaller. If it's, see the distance between the two, the top, the full line is delta y, the bottom line is dy. So it becomes perfectly, they are becoming almost the same when we get closer to that. So when q approaches p, then delta y approaches delta dy. So it's used for approximation purposes. When you take when this is happening, when is q approaching p? When that happens? When what happens? Q approaches p if okay, Sterling, the tangent line is not something I get. The tangent line is something I want to discuss. All I want is that the tangent line at the point P only touches the curve at the point P. It cannot cut it into two lines just at a point P. Okay, Sterling? Sorry. It keeps turning off. So I'm just comparing the secant line and that's very, very usual. Even when we start the course of limits and finding the derivative, we went through this. But this is a way to change the calculus into like numerical values. That's another. That's what Newton did. Newton did this analysis, and he changed it into a numerical value of uh, delta x as dx and delta y as approximation of dy. Even though they see clearly, you can see the difference between delta y and dy. Well, I decided to bring a line passing through P and Q, which is the secant line, and I decided to compare the tangent line at P. And then, because I know that the only line that has the dy and dx is the tangent line. You can't have otherwise. But PQ is not a tangent line. I cannot have as the the slope of that cannot be dy by dx. Because it's not tangent line, it is a secant line is a line which cuts the curve at 2 points. Okay, so hopefully follow me. So Q approaches P when delta x goes to 0. See, when you cut the delta x to smaller and smaller and smaller, then Q is approaching to P. That's what the concept of infinitesimal is. The concept of subdividing, where we're letting delta x to 0, to very almost a positive quantity, but almost negligible, nothing. Then that is theoretically delta y and dy are the same. Okay. Anyway, so I want to make sure, and I just want to summarize. I want to make sure you understand this. This is very non-calculus or pre-calculus stuff. The delta y, what we're saying is the value of the function at this point minus the value of the y at this point. So it is y2 minus y1. y2 is f of x plus delta x, f of x plus delta x minus f of x. That's what it is. Delta y means nothing but the difference of the y values. The difference of the y values of 2 points. Here is a y value, here is a y value. If we subtract them, we get delta y. But this means f of x delta x, and this means f of x. So the difference of the two. But that's number one. Number two, but dy by dx is f prime of x. So dy is the derivative times dx. This is another formula for dy. So in most of the books questions, they are asking us find dy and find delta y and compare how bad they are apart. All right. So for now, I know the drawing. I will not ask you a question. All you need is, I just want you to visualize what's going on about dy delta y. The dx and delta x are the same. But anyway, all you need is those two for now. And then we do linearization in a few minutes. Now let's do examples. Or on section 24.8 and page 763. In number 6, they are asking find the differential of each of the given functions. So find the differential. That's very easy. Differential of the differential dy, let's say dy of y equal to 3x squared plus 9x. They didn't give me, this is a differential formula, not a number, because they didn't give me x. So what is the derivative? Remember, dy by dx? dy by dx is 6x plus 9. What is the differential then? You multiply both sides by dx. Then you get dy equal to 6x plus 9 times dx. This is the differential formula, just like we said here. Just like we said here. This is the derivative times dx will be the differential dy. That, if you give me a number dx, given dx and x, we can find dy as a line segment, right? Very good. That's just another way of differentiation, except that we have to rearrange the dy and dx at the end. Number 10, we have y equal to 5 into 4 plus 3x to the negative 1/3. What's dy by dx? Just find the dy by dx, even though you want to dy. or you can just find the derivative and multiply by dx. I think is it 5 over 3, 4 plus 3x, 1 subtract from the exponent, times the derivative of the inside. This is what I got. So this is the derivative, which is 3's cancel, and then 5 over 4 plus 3x to the 2/3 is what dy by dx is, but they didn't want the derivative, they want dy as a segment. That will be 5 dx over 4 plus 3x to the 2/3. You just multiply by dx. So dy is that as a segment. We used to say dy by dx, no problem, it's the same, but they want dx now, just dy now. dy f prime of x times dx, the same. So here is dx, you can put it dx right there if you want. This part is a derivative, this is a dx. So I will do number one more, I think, like number 16 maybe. Why this is differentiation I am doing again, really, nothing new. It's hard, that's why I picked it. So this is like 3x plus 1 over 2x minus 1 to the half. The derivative of dy by dx is the derivative of the top, 3, times square root of 2x minus 1 minus the top times the derivative of the bottom, 1/2, 2x minus 1 minus half times 2 over 2x minus 1 square root with a square is 2, just 2x minus 1. So far, okay? So far, okay? Okay. And silence is agreement. So this is 3 root of 2x minus 1. So the 2's cancel then minus 3x plus 1 over root of 2x minus 1 over 2x minus 1. And then, you know, a minus b over c over d is simply ac minus b over dc. So 3 times the product of these two is 2x minus 1, because square root of x times square root of x is x. So this multiplication gives me that. This multiplication that is all over 1 here gives me only 3x plus 1 in brackets over this multiplication, as the formula says, is 2x minus 1 to the 1 and to the half is to the 3/2. That is to the half, that is to the 1. Okay, this is to the 1, this is to the half. When you add them, you get 3/2. So this is equal to 6x minus 3 minus 3x minus 1 over 2x minus 1 to the 3/2. 3x minus 4 over 2x minus 1 to the 3/2, or square root of 2x minus 1 cubed is dy by dx. Therefore, just dy is simply 3x minus 4 over 2x minus 1 cubed dx would be the answer. Did I confuse you, or are you following me? Okay. The next level of questions are asking you.
The denominator 3 over 3/2.
Oh, 3/2, yes. Thank you, Wissam. Yeah, you're right. I stopped writing 3 from here. Okay. Okay, thank you so much. And from here down, the questions are changed, like from number 17 and up. They are saying find the value of delta y and dy. So that's our interest on this section. So find the values of delta y and dy for the given values of x and delta x. So number 18, they say y equal to x squared plus 2x cubed, x equal to 7, and delta x equal to 0.01. So I think this is about finding delta y as a number, dy as a number, and comparing. So let's start the delta y. Delta y is easy. It doesn't need any calculus. Calculus is a concept of differentiation and integration. This has nothing to do with the differentiation. Delta y we have used before it. Delta y is simply f of x plus delta x minus f of x. What is f of x delta x? Let's find x delta x. What is x plus delta x? Which is 7 plus 0.01. So it's 7.01. So f of 7.01 minus f of x is 7. So what is it? So this is like 7.01 squared plus 2 times 7.01 cubed minus 7 squared plus 2 times 7 cubed. There is no calculus so far. So 7.01 squared plus 2 times 7.01 and cubed. I got 150,000. Is that what it is? 230.2423 minus 7 squared is 49 plus 14 to the power of 3 is 250,000. 0.47. Is that what we get? No, it doesn't make sense. This is more bigger, it should be, right? So I made a mistake. 49 plus 14 to the 3. That is okay. So let's do this. 7.01. Is it squared? Squared, yeah. Plus 14.02 the power of 3 is actually 200. Yeah. So then the difference between the two is 1911.1593. Right. Thank you. And then what is dy? But what is dy? Dy by dx equal to, let's find dy. We're done with that. No derivatives. What is the derivative? It is bring the exponent x squared plus 2x, reduce the exponent, times the derivative of the inside, 2x plus 2, right? So this is dy then is 3 times x squared plus 2x squared, 2x plus 2 dx. So here 3 times 7 squared plus 14 squared, 14 plus, this is 49, right? 14 plus 2, which is 16, times dx, which is 0.01. So 49 plus 14 equals squared times 3 times 60 times 0.01. Oh, something wrong with my calculator. What is that? What you got? Wasim, Wissam, 1905.12. Thank you so much, Arfan. Wissam, 1905.12. Thank you so much. So they're 1911.159, 1905.12. I tell you, delta x was 0.01, was it? Yeah. If we had delta x to be 0.000001, then these values might be so much closer to each other. Okay? Hopefully, you understand what I mean. Because on our analysis, we say that delta x and dx, delta y and dy are almost the same if delta x is almost 0, if delta x is almost 0. Or dx, they are the same anyway. If dx or delta x is equal to 0, almost 0, then the difference between the delta y's would be the same. Change in x, the smaller the change in x, the smaller the change in y is. So I think I probably will test you on this. Compare delta y and dy for given values of x and delta x and the function, of course. Okay. The other section I wanna, within the same section, they talk about linearization, approximations. The interest we have is to change our objective here is to approximate complicated, well, complicated is relative, complicated function using a linear equation, a linear function. This process is called linearization process. Okay. This process is called linearization. What we do is, usually it's very applicable in the labs. When you take a data from a complicated function, it is so complicated. If we know the derivative, it can make the complication easy. So
does they do that also for calibration?
Oh, for
instruments.
Yes, I think it's everywhere. The linearization is everywhere. I think it is most applied concept in engineering because it simplifies the complication, just like Newton's method. Remember, we had a complicated function to solve, but we changed it into Newton's method, iterative method, and then it makes it doable if we know the derivative. The linearization is, you're right, in precision of materials, in many engineering concepts, it's applied. As long as the approximation is kept, as long as the delta.
Is it the same thing they use it for method validation when they propose a method and when they want to validate it? I mean method of test, let's say, and when
Yes,
they want to
it could be
validate
used.
it.
Yes.
So it's the same as the linearity, right? The linearization.
Oh, the linearization is a big concept in mathematics. You can talk about
Yeah.
linearization of linear algebra concept in spaces like subspaces and so on. And it is a big thing. What we are doing geometrically is we have a complicated function. We're gonna fit a line which is a best approximation to that. So this is a line which is a linear function, right? But this is complicated. We don't know y equal to f of x. So we call it the linear function as L of x. So what we're saying is, to the best of our knowledge, if we are doing a close by neighborhood, if you in the neighborhood, the line and then the graph are the same, right? So this process of changing a complicated function into linearization, into a linear function is linearization, but it is applied everywhere. Like if you have a complicated function about population density, then that is hard to deal with. You using derivatives, you make an approximate linear function, or you can calculate the numbers so easily. Like you said, material precision or in validation of a complicated function, you wanna use a linear equation so it will be understood. Then you can use the linearization process, especially in the lab when you want a data set of x and y. If you have a big function which is too complicated, like in chemistry or in civil engineering, we have big formulas. We don't want to deal with them. If we know their derivatives, we can change them into L of x and then get our data based on that. So the same data we will get had we used the original but complicated function. That is the idea of linearization.
Can we quantify it?
Yes. Like in numbers, you mean?
Yes.
Yes, we'll find the function and then relate both functions. We can calculate how far or how close they are. Okay,
Thank you.
you're welcome. So the idea is the linearization function is L of x, which is equal to f at a plus f prime of a x minus a. So any function f is given f of x. L of x is its approximate linearization. L of x is given in such a way. Okay, you can easily verify that. Really, so if we take about I don't know, if we take a line here, a tangent line, right? If this is a and f of a, you can take about on the xy in here, you know, x and y as a point. So using the values of xy, what is a slope? Slope is actually the slope of the tangent line is f prime of x, the derivative, right? And then what is the change in y over change in x? We're going to equate it. The slope f prime of x at a would be f prime of a. At a, it is f prime of a, right? So delta y is, this is y minus f of a. I'm sorry, y minus f of a over x minus a. The rise is, I'm working here, you know, y minus f of a is the rise, and x, the x component of the second point minus the y, the x component of the y first point is that. So if you cross multiply y minus f of a equal to f prime of a times x minus a, and then y is actually f at a plus f prime of a at x minus a. This is y is f of x. So that is the approximation. Approximation is L of x. So is that what I gave you here? Yeah. It match? Yes. Therefore, the linearization of any function is f of a plus f prime of a x minus a. So this function, this curve, and this line are almost the same at around a, at the neighborhood of a. That's what we're saying. So we don't have time, but I will do an example. And then, like you said, we can compare when we use f of a number 5 versus L of number 5, and then we see the difference. Okay, but we don't have time. Technically, I should dismiss the class now. Is there any questions? If you have a minute, I could do an example. But I think it's okay. Yeah, okay. Okay, we'll do an example. So in question number, is it 18? Number 18. Oh no, we did number 18. So it says number 22, example page 764, number 22. They say find the linearization. Find the linearization L of x of the given function. At the values of a, the values of a. So we have some, the other ones are easier. I think number 22 is a little bit, it's the same anyway. They are easy in a way. To find the derivative, if it's hard, is what I call hard. But the derivative here is easy. So instead of this cubic function, right? I don't know what the graph would be like that. Cubic, is it? I don't know. If that is cubic function, no, it is cube root function rather. So I was right. So instead of the using the cubic function, the cube root function, we want to use the linear function. So that's what when they meant find the L of x. What do we need for L of x? L of x is simply f at a plus f prime of a x minus a. No big deal. So easy. Like all we need is f prime of a. So what is f of a? F of a is, f of x, f prime of x. Let's change f of x to 2 to the x 1/3, right? So then f prime of x is 2 over 3 x to the 2/3. So this is 2 over 3 1 over x to the 2/3. When x equal to, we need it with a. When x equal to 8, this becomes 2 over 3 1 over cube root of, well, you can use a calculator. Don't do it like me. If you want to do it like me, I take the cube root of 8 first, which is 2. 2 squared is 4. Cube root of 8 is 2. 2 squared is 4. So that's 1 over 4. So here it is actually 1 over 6, is it? Okay. What is f at a? F at 8. F at 8. I'm going to need f at a there too. F at 8 is 2 8 to the 1/3, which is 2 times 2, which is equal to 4. So my linearization or linear function for this approximation is f at a, which is 4, plus f prime of a, which is 1 over 6, x minus a, which is 8. So this is, here you go, this is, here you have it for the linear function. 1 over 6x plus 4 minus 8 over 6. And then you can even conjoin this. 1 over 6x, 24 minus 8, 16, is it? All right, I can't take because I have been talking for the last 4 hours. Okay. So this is the linearization of x to approximate, which approximates, that approximates the complicated function of cubic, f of x equal 2 cube root of f of x equal to 2 cube root of x. So add a equal to 8. Now we're going to talk about quantifying it, like compare quantities in terms of numbers. So like take a number, like this is the answer for you for this question. Did you get it, or did I go fast? Did you follow me? First find the derivative and then fill up the formula of the L of x. That's all I did. Right? So if you quiet, everything is okay, I believe. So this is my line. So let's take, let's compare results. Compare. Say we have to get close to 8. So what is f of 8.01 versus L of 8.01 is my question. I put 8.01 because I have to be close to 8 when I do this research. Yeah, I cannot just say, okay, what is f of 100, f of L of 100? They might be hugely different because we are talking about the close values of a. So what is f of 8.01? What is f? It is 2 times 801, 2 times 8.01 to the power of 1/3. In your calculator, it is 8.01 to the power of 1 divided by 3 times 2 is 4.0016659723. So 8.1 on the linear equation. As a linear equation, 1 over 6 times 8.01 plus, what is it, 8 over 3, is it? Oh, somebody said something. Yes, thank you. Let's do it with a linear equation, what we get. So 8.01 divided by 6 plus 8 over 3. It's actually 4.00166667. So it's very close, right? They're very close to each other. Do you agree with me? So L of x approximates f of x in this case, okay? So I will assign homework on Blackboard, or maybe if I have it, let me double check. Okay, the homework is for section homework of section 24.8, page 764, maybe not, 763. So I said from number 5 up to 17, from number 5 up to, well, numbers 5 up to 17 odd, and I need linearization question like 21. Do both of them, 21, 23, 21 and 23. Thank you. No, test, does it say week 8 or week 9 on the syllabus? Week 9 is now, not next week. It's a week after. We are in week 7 right now. There's no, we don't count the March break. I don't know, Michael, what are you asking? Okay, hold on. The test is week 9. We are in week 7 now. Next week we do lesson, more lesson. Okay, Mike, okay, I'll give the homework. Thank you. So the homework for that, okay. But is it clear about the test? The test is, this is lesson week. Next week is lesson week. You have March break. When you come back, I probably do a review and then give you the test, period. You get it? Hopefully. Yeah. So that's week 9. So we have time. For the homework of section, okay. Give me 1 second. Oh, for the homework of section 24.7, right, Michael? Oh, I'm lost. Oh, Wissam, it's already given, he said. I think I assigned it last class, Michael. You have it on the files, but I can go over here, right? Oh, in the first section, I already wrote it at the end, like right here, Michael. Or Strawberry, you're asking for the homework? Yeah. Is it clear? Thank you so much, Wissam, for thank you, Michael. Have a great day. Sorry to keep you late all the time. I say so. Thank you, Sivan and Strawberry. Everybody, have a great day. Thank you, Sam.
Thank you, sir.